All right, welcome to another video in the series, 5-minute practice series. This is part 2 of the third 5-minute practice worksheet we have, or part B, I could say, where we talk about the reason behind why you need UV light to produce vitamin D. Okay, vitamin D, you've probably heard that it's really important for immune system. It's a immune system modulator, and it is actually synthesized within our body in our skin. But you've probably heard that you need to get some sunlight, or you're not going to have your vitamin D. And there's actually a chemical reason for that. In fact, there's actually a Woodward-Hoffmann reason for that. And here is our precursor to the vitamin D skeleton. And here's a 6-member ring with diene in the middle. Hopefully you can see that can actually open through a 6-pi electrocyclic reaction. So maybe I'll add that in here, 6-pi. Okay, and then this is going to happen with UV light, which means that in this trying product that we see, there's going to be 6-pi electrons, so 6-pi molecular orbitals. In that 6-pi molecular orbitals, we're going to have to deal with UV excited promoted hormone. Okay, so that's going to be, hopefully it makes sense to you, it's going to be the pi 4 of the 6-pi electron molecular orbitals. So pi 4 will have 3 nodes. Okay, so pi 4 should look like, let's see, 3 nodes here would look like 1, 2, 3. Okay, so that's our 3 nodes here, and so it's good if I were to fill this in 1. Okay, that's how the nodes should appear, right? And this is what the, well, I should label this. This is pi 4 hormone. And this is what should be there after the ring opening reaction through electrocyclic reaction is done. Okay, so we want to show whether this process will happen through disrotatory or conrotatory process. So I'm just going to draw just this part of the ring. Okay, just for speed, so just to do this real quick, and I'm just going to show how the methyl group is up here, and then the R group, I'm just calling this the R group. Okay, and this is going to open like so, and when it does, we want to know if that's going to be disrotatory or conrotatory in the direction of the orbital rotation. So the orbitals should have looked like this. And this is going to open up, and when it opens up, it should look like, maybe I'll pi 4, right? So it should look like that. So in order for this to happen, the rotation of the orbital, it's going to have to be like this for that orbital, and then like this for that orbital. Hope that makes sense. To get the white orbital here, right, or I should say right there, and then for the other one, the white lobe of the orbital right there, right? So this is going to be conrotatory. Right, at the right chiral center, it's the p orbital is rotating towards the right, and then same with the other chiral center. So that's a conrotatory process. Okay, so that's how we end up with, let's see, this situation. All right, and that's indeed what we see in the product right there. Okay. The second part of this problem is asking for the mechanism for the 1,7 shift. So that's just kind of like a bonus question from going from this molecule to that. Well, let's see if we can draw just the arrow mechanism. So the pertinent part of this reaction is just going to be this going to that. I just extracted like this part of the structure. Okay, so hopefully that makes sense just for simplicity. So what's going on here? What we make the observation that there's a hydrogen missing from this methyl group, and then there's a hydrogen gained by that carbon. So let's see if we can depict that here. Okay. So that would do the 1,7 shift. Okay, it's actually an electrocyclic reaction. We won't ask you on the exam about like a 1,7 hydrogen shift, but that's actually an electrocyclic reaction mechanism, and I thought it might be a good practice of drawing arrows for that. But again, if you have any questions, let me know, and thanks.